Welcome back to the second part of today's lecture. So now we move on from point forecasting to something more. This will be some simple probabilistic forecasts, and we will walk through a few examples here. So let's move on here. Probabilistic forecasting. I mean, when you define it, it's not. I mean, not easy to define it because when you think about probabilistic forecasting, it's not the method that you use. I mean, the method is. I mean, all methods are probabilistic, most of them, except for the naive model. But even the regression model is probabilistic. You have the noise term, which is random. In this sense, it's probabilistic. So when you say about probabilistic forecast, we talk about what is the output of our model. And we usually think about the distribution. So some distribution is the output. But typically, we do not output the whole distribution, neither distribution function nor the density function if it exists. But typically, we output some quantiles. Now, quantiles are points, essentially. If you report one quantile, like in value at risk calculations in finance or risk management, this is one value. So the median is also a quantile. So is it already a probabilistic forecast? Well, I wouldn't say so. A median or a mean, in some cases, some symmetric distribution, they're the same. So it's still not. If you have two quantiles, then you can link them. There's a probability of observing a value between those two values, the two points. This is a probabilistic forecast. So probabilistic forecast is something that tells you more about the distribution than just the mean of the distribution or the median. So it's something more. Now, in general, another problem with probabilistic forecasts is that if you want to evaluate your model, then you don't have a probabilistic distribution, the actual distribution. You have one observation, one randomization of some distribution, which you are trying to predict. So you'll be comparing a predictive distribution or probabilistic forecast to the past observation. So you have just past observations and you have a predictive distribution. So kind of combining a distribution with just one number, comparing it, well, you need a way to do it, really. Now, in a series of papers, just roughly, 2 decades ago already, Tillman, Gniting, and co-authors, they kind of try to emphasize that when you are trying to build a probabilistic forecast, what you try to do is you try to maximize the sharpness of the distribution, how tight it is, but only if the predictions are reliable. Let me just spend a few words on this. So, so this illustration here, where we have at time t0, we have the price at this time t0. Well, what probabilistic forecast is essentially is this whole distribution represented as a density here, whereas the point forecast would typically be this white number, let's say the mean of the distribution here. So and of course you have several horizons up to t5. And the dots here represents the actual observation. So what we are trying to do here, we are trying to compare this dot with this distribution. That's what is evaluating probabilistic forecasts. Now, reliability, again, there are a few terms that refer to the same concept. Sometimes it's called calibration, sometimes no biasedness. And here we have references for these papers, and it's kind of a consistency between what the probabilistic forecast should tell you and the actual observations. It's simplest to explain in terms of the prediction interval. So if you have a 90% prediction interval, you want 90% of the observations to fall into this interval. Now, I've seen many papers, and some actually published in relatively good journals, where authors are claiming that they have a 99% coverage of a 90% prediction interval, and they say this is great. No, this is crap. We don't want 99, we want exactly 90. This is what we want. So here in this example, actually taken from one of Tillman's articles, you have the green line is some median or expected value forecast, point forecast, typical point forecast. The red dashed lines are the prediction interval for different moments, different hours of the week. This is essentially 1 week of data, of hourly data. The actual observations are either the blue circles or the yellow circles. If it falls within the interval, it's yellow, so it's a hit, you can say. If it's like here, it's outside, this is a miss, so it's blue. Now, what is coverage, empirical coverage? You just count the number of hits, divide by the total number of observations, number of hours a week in this case, and you get roughly 92% coverage. Okay, so this is not that bad if it's a 90% prediction interval. Okay? This is reliability. So perfectly, this should be 90% if this is 90% prediction interval. But of course, there may be some deviations, and then of course there are tests to test formally if this deviation is still acceptable or not. And I'll talk about them, I think, tomorrow lecture. Sharpness, the second concept. You want them to distribution to be as tight as possible, because if you have a very wide distribution, it's no information in this forecast. So optimal forecast would be actually a point forecast that with probability 1 would give you the right observation. Well, it's not achievable in practice, but that's what it really is. So if your probabilistic predictions are reliable, now you want them to be as tight as possible. Okay, you don't want to have them as tight as possible if they're not reliable, because this is not good forecast. So this is sharpness. So yeah, that's the two main concepts. There are a few more, but I won't go over all of them. Now, one of the easiest ways to go from point forecast to probabilistic forecasts is to post-process the point forecast. Now, post-processing is a term used in many contexts. I mean, it means you have something in the beginning, you do something, and you get something else out of it. But it's in this case, we have the inputs of the point forecast, like here. We do something to them, we post-process them in some way, and then we have probabilistic forecasts or quantile here forecasts. The illustration here is from our, no, not this article, actually this one here probably. This is the Arek will talk about it tomorrow more about this package in Julia. The idea, the part of it is post-processing point forecast. Now let's see what are the simple ways to do it to obtain probabilistic forecasts. So one of the classical assumptions in statistics essentially is that errors are normally distributed. So if you assume the model is right without checking it, you can say, okay, all we have to do, we take the predictions, the prediction errors, over some calibration window of our probabilistic forecast. So now we may have a situation where we actually have some calibration window where you get the point forecast. So we have the p hats, p. Then here we can have the errors, epsilon t's on some window. And we are working now with this window. This is this S here. Now we make a probabilistic forecast for the next moment in time. Okay, so we have the point forecast. We post-process them to obtain the. We have the forecast here. This is just to fit the point forecasting model. We have the forecast here, point forecast, and use those errors to approximate the distribution. So in this simple model, we take the prediction errors, we fit the mean, the sample mean, the sample standard deviation, and then all you have to do, take the quantile of this prediction is essentially based on your point forecast plus the mean plus a quantile of rescaled by standard deviation, a quantile of standard normal distribution. Okay, this is very simple. So this is essentially what you say. You are here, you make a point forecast for this moment in time, and then you have the distribution with a mu and sigma, and they define how spread or where is the distribution. Okay, that's very simple. Historical simulation. Okay, this is a term that is used in risk management and finance, essentially. It goes back, probably this is the first publication where it was used. Maybe it was used a bit earlier, but it's 1996. The idea is here that this is a model independent in the sense that we have only the prediction errors. So we take the prediction errors. So we have we have the prediction errors again on some calibration set of where we have those, where we already have the point forecasting model working. And we take the empirical or the sample quantile of those errors. Essentially, you can think of it, you take a histogram maybe on the next slide. So you take your errors, epsilon t's, and you make a histogram of those. And this is your approximation of the predictive density, okay? Or the predictive density around, in the middle you would have here your point forecast, p hat t, okay? That's the idea. And then, of course, this can be asymmetric because you can have, let's say, more negative errors than positive errors and so on. Okay, so there's no symmetry here assumed. And this is the simplest thing you can do. And this was called in finance historical simulation. In some texts, some articles, you may find the name bootstrapped residuals. There's a subtle difference, meaning that in historical simulation, you use exactly each error once. Okay, you use, I mean, I don't know, you have a calibration window of 100 days where you have the prediction errors, the point prediction errors. Then you exactly use those 100 values to make the histogram to approximate the predictive density, predictive density. In Bootstrap, you actually sample from the errors. So sometimes you can take two errors twice, the same error twice, and some other may not sample. But in the long range, I mean, this will give the same results. So Bootstrap is a slightly different than historical simulation. Actually, it's more general. You can bootstrap in many different ways. So historical simulation is a very simple way. It's as I said, used in finance. Now, something which is related but comes from the machine learning or computer science literature is conformal prediction. When you look at the original papers, maybe it's hard to grasp at the first moment, but really what is happening is illustrated here in those two histograms here. Now, in historical simulation, as I said, you build a histogram of epsilon t's. What you do in conformal prediction, you build a histogram of absolute value of epsilon t's. So kind of you take your distribution and you fold it. So you have twice more observations, but at the cost of having a symmetric distribution, because then you kind of unfold it and then you have symmetric distribution. So this is the basic way how conformal prediction works. And of course, again, you may have many variants, but this would be called an inductive conformal prediction. Main difference. So either you can, if you have small samples, conformal may be better off if the assumption of symmetric predicted distributions is not a big problem for you. If it is, then don't do it. Yeah. So why is it smoother? Well, because you are folding it. So all the negative errors become positive, and then you have a better approximation of 1/2 of your distribution. But it's assumed that it's symmetric. Then kind of unfold it, and that's it. So here in this orange, it's a mix of the red ones and of the yellow ones. And then you unfold it to get the full distribution. As you can see, this is actual data here. So this is the original epsilon t's here. And like this bar here is a bit lower than this bar. Whereas if you collect all of them, this bar, this orange one, is in the middle between this height and this height, actually. Okay? But that's what happens here. So two very simple ways to produce probabilistic forecasts out of point forecasts. All right, it's time for you to show it. And I don't know, you want to do it in Colab this time?
I think we can. So maybe I'll also show how it works in.
Okay. Paul, can you check if you see the screen this time? You can see it. Okay.
Okay, so now we will do it in actually in Colab. So if you click on any of the links or badges,
maybe
of Google Colab,
first you go to my web page, slide down, click on the GitHub repository. In the GitHub,
you can actually you don't even have to go there. So already here you can just click on the link and it will go directly to the Google Colab. And so here, if you have a Google account, there's no need to install anything or just run it as is. So as before, we will import the libraries that we will be using. So And again, so some snippets will be the same as before because we will use some of the same methods, load the same data sets. So this is the same data that we used before. We will also use the same week, and we have to prepare some explanatory variables because to use any of these uncertainty quantification methods, we need to have some point forecasting model to begin with. We need something to post-process. So we will start by creating these variables for our regression model, and again, select the length of the training window. And then we can generate our forecasts using ARX model. So this is up until now, everything else was already done before the break. We will remove the days without the forecast. So one difference is that now we actually run the linear regression model for the entire data set. And for this week, we will only produce these probabilistic forecasts. So we also need to have some past errors for that. So we need to have more point forecasts than just a week of them, right? Because we need some out of sample errors to estimate the distribution. So right now we have data from the beginning of 2023 to the end of 2024, so full 2 years of data. And now we will find the index that corresponds to this first date of our forecasting period. And to start our post-processing, we need to define some functions that will perform the methods that Rafał told you about. So let's start with historical simulation. So the inputs will be the forecasts, the observations, and alpha, which will denote the confidence of our prediction interval. So it is very simple. So we calculate the errors as the differences of forecasts and observations, and then we will derive two quantiles, the lower and higher one, of these errors, and this will correspond to 1 minus alpha divided by 2. So for example, if our alpha is 90%, the first one will be 5th percentile, 5% quantile, and the higher one will be 95th percentile. So that between them we have 90% of the values, and we will return the lower and higher quantile, and then we will just have to add our point forecasts to both of them, and this will give us our prediction interval. And so next, let's go with conformal prediction, because it is very simple, and we'll now see exactly like the differences between both of them. So now, instead of calculating the errors as the differences between forecasts and observations, we take absolute differences, so absolute errors of the forecasts. And we just have to take one quantile, which will be the alpha quantile, and then our prediction interval is symmetric and constructed from minus Q to Q. So you can see now that if we build these prediction intervals around the point forecast, the historical simulation one can be not symmetric around the prediction, while the conformal one will always be a symmetric prediction interval with respect to the point forecast. And then definition for the normal model. So we will once again take errors, estimate the standard deviation, and then take Q as a specific quantile of the normal distribution and build our prediction intervals around this quantile. So now we need to specify some parameters. So the length of the calibration window and the confidence levels that we're interested in. So here we will use half a year of past errors to estimate our prediction intervals, and we will construct 20%, 40%, 60%, and 80% intervals. So here we have a simple loop over the confidence levels and over the models, and we create appropriate columns for our data set, which will store the lower and upper quantiles or lower and upper bounds of the prediction intervals. And then we generate these prediction intervals. So we take lower and upper bounds from historical simulation, conformal prediction, and normal, and then we add them to the forecast that we have. So here on the right-hand side of the assignment, you can see that we always add the prediction interval to the specified, to the derived bounds for the of the prediction intervals. And then we remove the days without the prediction intervals by just dropping the values that have that are nonce. And you can see that once again we have a week of our data in May that we had previously for our point forecasting. So now we can plot this probabilistic forecast that we obtained, and we can see. So let's start with conformal prediction. You can see here clearly that. So maybe I'll quickly tell what the colors mean. So the more intense the color, the higher the probability. Maybe not the higher the probability. The smaller the confidence of the prediction interval. So the dark color corresponds to the 20% prediction interval, and the lightest blue, between 40 and 60, and the lightest one corresponds to the 80% prediction interval, so between 10 and 90. So, okay, so now you can clearly see that these prediction intervals from the conformal prediction are centered around the point forecast. They are symmetric around the dark line, and the dark line here is just the point forecast that we have, the AR from ARX model. And now when we take a look at historical simulation, you can clearly see that we even have some cases where the this 20% prediction interval, the innermost 20% prediction interval is outside of the is shifted from our point prediction, due to the fact that this allows for non-symmetric intervals around the point forecast. And now to compare historical simulation and conformal prediction, maybe on the same plot. So we will now only use the 80% prediction interval, and well, here you can also, this highlights a bit this non-symmetric behavior in some cases. So for example, clearly here you can see that the difference for the lower bounds of the prediction intervals is higher than for the upper bounds of interval here, right here. Okay, so this was the quick intro to uncertainty quantification from the ARX model.
Okay, thanks. Thanks. Okay, we take the question after the next part of the talk. Okay, so okay, one more thing just to remember. Of course, what Arab was showing in the code is that we need the errors of the model, which is of the model that around which we build the probabilistic forecast. So we have the point forecast of the model. It was autoregressive model. We had the model errors of this model, and we added then those predictions, the probabilistic ones, to the new predictions of the same model, because kind of we are trying to catch how wrong our model can be based on the recent past. So this is what these epsilons t's are here, and how we build these histograms. So it has to be the same model. You cannot use the predictions of a different model, like epsilon t's errors of a different model, to build a forecast around a different model's forecast, point forecast. That wouldn't make sense. Okay. Okay. Last thing today, forecast accuracy. So just very briefly, I mean, for point forecasts, we have all heard about the mean absolute errors, mean squared errors, so I won't go into it. There's the mean absolute percentage error, which is MAPE, which is very popular in some contexts. We've even seen it today. So as far as load forecasting goes, since loads are very far from zero typically, at some high level, then you can use MAPE. However, if you have really huge fluctuations, like I don't know, you go from 1,000 to 2,000 in observations, then MAPE already is problematic. If you go with the observations close to zero, it becomes really bad function, or negative, it's undefined essentially. So one of the other ways to kind of normalize this or normalize this MAPE is not to divide it by the value of a single point, but by an average over, let's say, a day. Okay, So this is kind of sometimes it's called a daily weighted MAE. You can do it also weekly weighted. So this would be an average over a week. There's the symmetric MAPE, which tries to be because MAPE itself puts a heavier penalty on negative than positive errors. So in a sense, it's already kind of problematic in this context. You can try to correct it by doing something like make one of those symmetric MAPEs that has different specifications. You have to be careful because sometimes in the denominator you may have an absolute value of the sum of the actual value and the forecast. Sometimes you may have the sum of the absolute values defined differently in different texts. Be careful which one you are using. Still, this is not really a good measure, and although it's used in some competitions, but it's not really a great measure of what is happening, especially in price forecasting, because if you have values close to zero, so then both these are close to zero. Also here, you're dividing by something very small, and you can get really meaningless results. Scaled errors, we've heard already also today about them. The difference between scaled errors and relative errors essentially is what you are using as a benchmark. So with relative errors, your benchmark is the out of sample period, the performance of some model in the out of sample, typically a naive model. Whereas in scaled errors, it's the base here is the MAE of, MAE or whatever, of a naive prediction on the training set. Okay? So this is the main difference between scaled errors and relative errors. With scaled errors, if you have models which use different calibration windows, with different training sets, then you cannot really use scaled errors because they will be defined on different sets. So then in this and since we are quite often using different calibration windows in our models, we prefer to use relative errors. And relative errors are nice because they kind of give you some numbers which are around 1. Especially, essentially, if you are lower than 1, then you are better than the benchmark. If higher, then you are worse. And of course, you can have a relative MAE, you can have a relative MSE, whatever you like, essentially. So this is a simple way to kind of report an error in relative terms, and I would say I think it's better than the MAPE. Okay. Coverage. So how can you measure the coverage? And let me just quickly say, okay, this will be a test of how to test whether the prediction intervals are reliable. Okay? So I told you that a good probabilistic forecast is a reliable, it's very sharp, so narrow, but reliable. Okay, so how do we measure it? With the so-called unconditional coverage is what we have already done. We have a series of hits and misses. So a hit when we are inside the prediction interval, a miss when we are outside. And in general, we should match the nominal coverage. So this is a 90% prediction interval. We want 90% of the observations to fall into the prediction interval. In different articles, you may find something like prediction interval coverage probability. Well, this is essentially it. It's the sum of it's just an average of or sum of this. You can, the sum, but divided by the length with an average. You can have an average coverage error, so the difference between the nominal one and this empirical one. Reported different papers. Just be careful what it is. Now, how to test it? The simple, again, we kind of go back to the financial literature and or risk management literature when valued risk tests became popular in the 1990s. And this is a paper of Kupiec from Journal of Derivatives. How to check whether a series of 0 and 1s has the right coverage. The idea is to use a likelihood ratio test. So in the denominator you have kind of the relationship to the percentage of hits. The C is the nominal, so this is like a nominal number. So what you would want to have. This is what you actually the P's are what you actually observe. So this is the empirical part. The ratio of this, it has been shown to have a chi-square distribution with 1 degree of freedom. So you can easily test whether this is a deviation. So like we had before, empirically in this plot, we have an empirical coverage of 92%. So the question is it okay, or is it already deviating too much? This is what this Kupius test actually is testing. It is testing whether this 92 is still okay, depending on the size. So this is a very simple test. An extension of this test is something which is called conditional coverage. And it uses also the concept of independence. Now, the Kupius test, this one here, it just looks at the number. So if all the yellow ones were here and all the blue ones were here, it wouldn't be a problem, as long as it would be 90%, which obviously is not good, because this would mean that here our model was really bad and here was really great, or maybe too good even. Okay? So we want these hits and misses to be kind of show it independently at different places, randomly scattered, we would want them. Okay, so let's say for simplicity, the blue dots, the blue circles would be randomly scattered in our interval. And this is essentially what is independence in this context, what Christopherson published in International Economic Review. So the Kupius doesn't care about the clustering, but we should care about them. So the independence test, I'm not providing here the formulas, but you can just, as a reference, you can have a look at this, and it's implemented in many different software, so you can just use this test. It just checks whether there's no one step ahead dependency between the. So if you had a kind of a blue dot at this moment in time, and the next one is also blue, the likelihood of this is not very high if it's only 10% of blue dots in your series. So you have to be careful. So if you have like blue, this means really bad. Okay, this would probably not pass the independence test. Now, what is conditional coverage? It's joint and unconditional coverage plus independence. And this is actually how it's calculated. So you have the likelihood ratio for the unconditional coverage, for the independence, and this is something we call conditional coverage. This is chi-square is 2 degrees of freedom. Again, very easily can be tested. Okay? So for simplicity, if you want to measure the goodness of fit of your predictive distributions, I would suggest to run the Kupius test just to get the coverage, or maybe the Christopherson if you want to be a bit more advanced, and then check the sharpness of your distribution, so how narrow they are. But you need some kind of an assessment of whether you get the right probabilities, whether the predictions are reliable or not. Okay, moving on to sharpness. CRPS, we've already heard about it. This is the standard metric for evaluating probabilistic forecast, but the definition is based on for a continuous distribution. So in most cases, we won't have a continuous distributions, especially in the previous two cases, we had the historical simulation conformal prediction, we have only quantiles. Okay, so we have to approximate it somehow. But in general, this is a good measure. It's a good measure in the sense it's a so-called proper scoring rule, meaning that the true distribution is an optimal kind of solution for this measure. So if you plug in the true distribution, this would be the smallest essentially. If we work with a set of quantiles, not a continuous distribution, then we approximate it. And this is essentially the formula for approximating it, where PS is the pinball score. We've already heard about it again today, but the formula is here. Okay, let me just quickly check the pinball score. What it is? It's a function of the quantile, the nominal quantile, the quantile prediction, and the observation. So if Q is 50%, so if it's the median, you have a kind of like an absolute value essentially function, meaning that if you deviate from, so if your error is the difference between the quantile and the prediction, the actual value is 0, then it's 0. But if it deviates one way or the other, the penalty is similar. Now, if you go to low quantiles, it tilts one way. If you go to high, it tilts to the other way, meaning that for a 5% quantile, if we are really bad on this side, the penalty is very small. But if we go here, the penalty is really large. Okay? So this is how the pinball score works. There's a penalty for exceeding one. I mean, it's an asymmetric score function. The absolute value, the mean absolute error is a median. It's this one, is the blue one. So you can write it compactly using the characteristic function, meaning that if this is true, then this is 1. If not, then this is 0. Or if you write it out explicitly, it's this one exactly. Okay, and this is plotted in this plot here. You may have heard or seen different names: quantile score, check function, lin, bilinear, newsboy loss. We even saw a newsboy on one of the presentations today. So yes, this is different names, is the same thing. So typically you would report later on some kind of an aggregate pinball score. If you do it across all quantiles, you approximate the CRPS. So going back one slide, you typically would choose an equidistant and dense grid of quantiles or probabilities here. For instance, quite often we do a 99 percentiles, like in GAFCON competitions, for instance, the 2014 one. So you, given this grid of 99 percentiles, you calculate the pinball score, you sum it up or kind of average it already, and you get an approximation of the CRPS. Okay, so this is a measure of how the predictive distribution works across 99%. So kind of a pretty good approximation of what is happening there. Now this scaling factor number 2 here, this red 2, sometimes it's just omitted, but it doesn't really matter. It's just a number. We want, if then we compare a pinball score of one predicted distribution with a pinball score of a different one. So whether just rescaled by 2 or not, doesn't really matter. But be careful, some papers use it, some papers do not. Many do not mention what they are doing actually. So then if your results, your pinball scores are twice higher than in some other paper, doesn't mean that your models are twice worse. It may mean that if you just use a different specification for the function. Okay. And once we have forecasts, if we say, okay, so what Arek even showed previously, we had an MAE and you have one model which was an ARX and one was a neural net, and one had a lower MAE or one had a higher one. Okay, is it significant, we may ask? And this is in econometric statistics, this is the most fundamental question. We have a model that gives you a smaller error. Is it MAE or MSE or any other error? But is it significant? It may be just a kind of random result, this slightly smaller value. So the most popular test for predictive performance is the Diebold-Mariano test, sometimes called the DM test, just from the first letters. So you have some score function. The score function actually can be the absolute loss, it can be the square loss, but it can be the pinball score, it can be the CRPS. So this concept works both for the probabilistic forecast and point forecasts. Okay, so this is a test for unconditional predictive ability. The variance, for instance, Giacomini-White, which is so-called conditional predictive ability, meaning that you take into account parameter estimation uncertainty. Okay, so if you are better off using the Giacomini-White than the Diebold-Mariano. The differences are not huge. I mean, also in the results, but better use it. And this is kind of comes back to the windows that I've been showing. I'm telling you that rolling windows are better than extended windows. And one of the reasons is that these type of tests, they can be used for both nested and non-nested. Nested meaning like one model is a simplification of a bigger model. So you have like, I don't know, 20 regressors, but you just take only 10 of them. This is a nested model. Some tests can work well or not on such models. And these two, they work as long as the window does not grow in sample size, meaning that fixed windows is okay, a rolling window is okay, but an expanding window is not okay. Okay, so that's one of the reasons why we should do it. You may have seen some papers which use different models for predictive performance, and one of them is so-called model confidence set. It's very similar to the DM test, but it uses Bootstrap. Okay? Bootstrap, you remember pulling the past values to approximate the test statistics. So we are not assuming some distribution of it, kind of asymptotic results, but we are building an empirical estimate of the distribution to kind of get a more accurate results. Of course, this means it will take much, much longer to get the results. You would have to run this estimation yourself. But okay, this is very similar. There's also forecast encompassing. It's kind of saying that the forecast of model 1 do not include more information than those of model 2. A different concept. I don't want to go into it, but you have references here. You can have a look what they really mean. Kind of the, let's say the base level is you run the DM test, the Diebold-Mariano test, and this is already not bad. Okay, so the Diebold-Mariano, what does it do really? If you know a bit about testing and the Z-test, it's an asymptotic Z-test, and the null is that the mean of the loss differential series, and this is this guy here. So essentially, you have one. Let's say your score function is an absolute value. So you have an absolute value of model. Let's call it 1 here, and absolute value of model 2. Okay. So you, for each point in time, you take a difference between 2 errors. Okay, model 1 and model 2. As I said, it can be the absolute value, the square, the pinball loss. You can use different score functions. Now, what the Diebold-Mariano statistic does, it calculates the mean of this guy and the standard deviation of this guy. We scales but by the sample size. T is the number of observations. And now the null hypothesis that of no difference is equivalent to saying that the expected value of this sequence is 0. So no. And now you are testing it against 2 alternatives. One alternative, this is typically the typical setup. So you would test it against the alternative that this expected value is negative, meaning that when can it be negative, this guy here? When S2 is larger than S1, right? Both of them are positive because they are errors, so they'll be positive. So if S2 is larger, so larger errors means model 2 is really worse, right? So what the test does, it compares them. The asymptotic distribution is normal, so then just take a normal distribution, and if this DM statistic is very low, you cross the critical value, you essentially reject the hypothesis of no differences, and you accept this one, that forecasts of model 1 are better than those of model 2. Then you do a kind of the opposite test with this alternative hypothesis, and you are testing whether model 1 is worse than model 2. And this means that in this range, you reject H0 in favor of this hypothesis. Okay, so you do it twice for the 2 tails. And because of the intraday dependence, the structure of prices in during the day, there's serial dependence. So they are not just correlation there. You cannot use the test if its data is not stationary and there's some dependence like this there. So you can either do it for each hour separately, optimally for business days separately and holidays separately, or you can do it jointly. So take some kind of a measure where you take the errors to some power, and this R can be typically 1 or 2. So absolute or squared. So you kind of an average error, the sum of the errors over the whole day. Okay. In this case, you kind of get rid of the each hourly dependence, and that's how you run these tests. Remember, final thing is that the DM compares forecasts, not models. So if you are a purist, this is very important that you say that the forecast of model 1 are significantly better than the forecast of model 2, not model 1 is better than model 2. That's kind of a different conceptual problem. Eric, and now Eric will show you the snippet which shows how to
yeah.
You want to open the column? I don't know.
No, it can be here, I think. Yes, great. Okay, so now we will quickly use the models that we worked on with previously, so the autoregressive model and the Holt-Winters model, and compare whether they are, compare them against each other and against the benchmark using the Diebold-Mariano test. So once again, we will load all of the necessary packages, the data set, select the starting. So here we will, here we first select the explanatory variables for our models. So create the lags of 1, 2, and 7 days. Then we will generate the naive forecast. So the same thing that we did in the first during the first notebook. Then again, the functions for hot winters, they are all the same as previously. Specify the parameters, so the seasonality for the hot winters model and the window for both ARX and hot winters models, and prepare the input and output data for the forecasting models. And because of the fact that of the problem with non-stationary errors, if we were to take all the hours jointly, like the errors for each hour as a single time series, we will now stick to just 1 hour of the day, and we selected the 7 p.m. here. And so we generate the forecast with autoregressive and hot winters models. I'm not sure about this. Okay. That's just a warning not to worry about everything runs anyway. So okay, so we generate the models, we generate the forecast with autoregressive and hot winters. We then remove the days without forecasts, and in the end we have the data once again corresponding to 2 years of forecasts, but all forecasts now are for the hour 19. And then comes the core of this notebook, so the implementation of the Diebold-Mariano test. So what we'll take the observations, the forecasts from the first model, and the forecasts from the second model. We will first compute the loss differential. So this is this difference between the absolute errors of the first forecast versus absolute errors of the second forecasts, and calculate the test statistics. So first we calculate the mean of this loss differential series. Then we calculate the standard deviation. So here, this optional argument d of 1 tells us that we already have 1 degree, that we have 1 degree of freedom. So this basically means that we'll use Bessel correction for the standard deviation. And then our test statistic is the square root of the size, our sample size for the errors, times the mean divided by standard deviation. And we then derive the p-value of our tests from the test statistic, which is the survival function. So 1 minus the cumulative distribution function of our test statistics, return this p-value as a result of this function. So now we will calculate, having defined this function, we'll calculate the test matrix. So this will be, so we have 3 models, naive, autoregressive, and hot winters. So what we will do is we will compare each pair of these models. And as Rafał said just now, we do 2 tests. So first we compare whether the forecast, whether the second forecast is significantly better than the first, and then whether the first forecast is significantly better than the second. So here we loop over these forecasts. If F1 is different than F2 because we don't want to compare the same models, the same forecasts, we run the DM test and set it in this set the p-value in this matrix. And then we can plot this test matrix. And here what we will do is we will create like a custom color map so that it will be easier to analyze the results. So if it is in a greenish, if the colors are greenish, then it means that they are below 5% significance, that the p-value is below 5%. Above 5%, but below 10%, it will be kind of reddish, and then above 10%, it will just be black, meaning that there is no significant that the model is not significantly better. And now when we plot all these values, what we can see, we can now compare these models. So maybe let's take a look. So we have Holt Winters and naive. So we can see that there is 5%. Well, we are at basically the significance level of whether the Holt Winters is better than the naive. But for the autoregressive model, we have a p-value below 1%. So it means that we can be quite sure that the autoregressive model is significantly better than the naive forecast. For all the other combinations, you can see that the values are definitely not highly above the significance level. And this is to be expected, right? So that the naive model is not, so for example, here, 1 means that for sure the naive model is not significantly better than the autoregressive one. And to perform a kind of a sanity check of whether we got the results that we expected, we can just print also the mean absolute error of the forecast to see how it looks like. And indeed, we can see that the autoregressive model was the best one in terms of mean absolute error on this test set, and the naive performed the worst. Yeah, and that would be all about the DeBuilt-Mariano.
Yeah, I guess this is essentially it what we had to present for today. So I think it was the last slide. Yes, essentially, yes. So if you have any questions, this is the time to ask them. The mic is here. I can pass it on.
Is there any statistically significant number of samples that you need to generate?
If I mean, in general, okay, if you have very few, the probably the results will not be significant. I mean, it will be really hard to get something significant. So, yeah, but if you have okay, then you become into problems with sampling. If you have really a lot, like a few thousand, then it will be again a problem with this. So, but in a kind of normal setting, like I know 1 year of forecast, this is a kind of a good range. So it's not a problem. Yeah.
Like instead of using the complete 1 year, we kind of group them based on, say, for higher prices, we group, just take the high prices one, or maybe, similar kind of days, we group them.
I'll talk about it a bit tomorrow. Yes, it can make sense. Yes, I mean, one of the differences will be working days, holidays, weekends, holidays. Another would be peak hours, off-peak hours. So there are many ways to group and analyze separately. But then, of course, by analyzing separately, you have smaller data sets. And then the question is whether it makes sense. Yeah.
Thank you.
Any other questions? And like the load data, does the price data exhibit any patterns? So how do you identify them and deal with them?
Well, okay, in the simple models that we have shown today, it's okay. We do not care about the long term so much. Okay, tomorrow I'll talk about how we can take care of it. But in general, if you forecast for the next day, you don't care so much about the longer term patterns. Okay? The short term is usually taken care of by the dummies, the daily dummies. This is the simplest way to do it and actually quite efficient. You could use, I mean, Fourier decomposition, but it doesn't make much sense in this context. You need at least 3 Fourier terms to get kind of a weekly seasonality working, so it's not a big deal. To some extent, if you are using load forecasts, they have seasonality already there, so you can use that. You can use, for instance, the number, if you want to think about a kind of a longer term, you can think about the number of daylight hours so over the year that will change in some sense. So there are different ways to take it into account. In the simplest models, typically we do not care so much. We take only the short term is important. So we're getting the weekly seasonality is important because sometimes it's not enough what you get from the load forecast or from renewable generation forecasts.
Yeah.
A probabilistic forecast is better in the short term than point forecast because probabilistic is usually used in the like medium long term, right?
No, I mean, why? It can be used at any for a forecast horizon. It's not, you cannot say it's better or worse. I mean, okay, you can, if you have a probabilistic forecast, you can derive a point forecast from it. If you have the whole distribution, taking some characteristic of the distribution is possible. So in this sense, probabilistic is always better than a point forecast. But getting it right is much more difficult than getting a point forecast right. That's the trade-off. But in the short term, yes. I mean, I'll show tomorrow some examples where actually trading in the day-ahead market based on probabilistic forecasts is much more profitable, by 20% roughly, than just trading on point forecasts. So that it makes sense to use probabilistic forecasts. So this would be kind of this economic value, financial value of forecasting, because so far today I was discussing more the statistical, let's say, correctness. So the errors, the tests for the differences. This is the statistical part. Now you can kind of move on to the economic part. So what is the impact of these errors that you are making on your profitability?
Any other questions?
I got one more question. I'll probably look at it. Is there any advantage, I mean, you see issues with limiting a probabilistic forecast to a shorter time frame in terms of, I guess, outcomes, limiting that as opposed to extremes, you know, if you wanted, you know, the highs and lows would be larger data set, but the honing on the mean, taking more, say, recent sample size. So I'm thinking probabilistic forecast using what it is, for example.
Okay, as I said, getting the probabilistic forecast, a good probabilistic forecast is much harder than getting a good point forecast. So in this sense, if you have a very short time series on which you train your model, you're probably better off just doing a point forecast. But if you get the probabilistic forecast right, I mean, it gives you the full distribution. So just gives you more information. The question is whether you can use this information. And this is the kind of the next step. So can we, I mean, this is something I've been discussing with practitioners for a number of years now. I mean, quite often I approach them and ask them if they know what is probabilistic forecast. They sure they know. If they use them, yes, of course they do. And then I ask, how are you using them? And then this is a difficult one, the killer kind of question. In most cases, well, we get a better intuition, but getting into kind of algorithmic terms is very hard. And what we've been trying to do with our group is to find algorithms who actually could automatically trade on probabilistic forecasts. And we show that this actually is possible. It gives you much more information. It gives you better decisions, trading decisions. So this can be done. Returning to your question, yes, I mean, in many cases, you won't be able to get the reasonable results because even in this post-processing with historical simulation or conformal prediction, you need a training set for your point forecast model, a training set for your probabilistic forecast model or the post-processing. Okay? This may not be enough if you don't have enough data, especially if the dynamics of whatever process you are forecasting changes dramatically, then you may have a problem. But again, I will talk about tomorrow about how can you overcome these kind of structural changes in the data to some extent.